Okay. So I hope I'm completely audible.
Yes, yes, you are right.
Yeah. Okay.
You
Thank you.
have been.
Yeah. So yeah, today we'll be talking about the duality theory. So last class we had covered sensitivity analysis. This week we will cover duality, as well as we will also delve into the transportation, transshipment and assignment problem. So this one class I'm just keeping for the duality, and okay, I hope you can understand whatever I'm going to teach. In case you are not able to understand, please feel free to interrupt. Okay, so there are a few terms which you need to know before we talk about duality. So just like in LP, we had learned about standard form, right? While solving a simplex method, the first step is we have to convert that LP into a standard form. So similarly, there is something known as a normal, or symmetric, or we call it canonical form of, let's say, a max problem. Okay. So what is this? So any maximization problem in which your variables are required to be non-negative and all the constraints are less than equal to constraints. So all the constraints, if they are less than equal to constraints and variables are non-negative, then the problem is called a normal max problem. Okay. So that means that it will look like maximize z equal to, let's say, c1 x1, c2 x2, like that till cn xn, subject to a11 x1 plus a12 x2, like this till a1n xn has to be less than equal to b1. Similarly, a21 x1 plus a22 x2, like this till a2n xn is less than equal to b2. And let's say you have m constraints, so a m1 x1 plus a m2 x2, like this till a mn xn is less than equal to bn, and x1 x2 xn are all greater than equal to 0. So then this is your normal, a general normal, or a canonical, or a symmetric maximization problem. Same goes for a minimization problem. Okay, so I won't write it. So a normal form of a minimization problem. Okay, in this case, all your variables are again required to be non-negative, but this time the constraints are going to be greater than equal to type. Okay, then the problem is called a normal minimization problem. Okay, so this was just a terminology that I wanted you to know. Okay, now we will talk about the concept of duality. Okay, so usually when you would be like learning it in different other classes, or maybe from the textbooks, you will see that they usually give you a very what should I say, a very bookish definition, and sometimes that kind of confuses students as well, that why are we solving dual models, or why is dual even needed when we already have a maximization problem or a minimization problem. So here I want to give you the intuition behind learning the duality theory. Okay, so let's say there is some company X and it has a product mix problem, where your problem for the company is, okay, So the problem is max Z is equal to 300 A plus 250 B subject to 2A plus B less than equal to 40. Okay. So let's say this is some machinery time constraint. Similarly, A plus 3B, let's say that is less than equal to 45. Okay, and that's some labor hours constraint. And let's say A is less than equal to 12. So let's say this is a marketing factor constraint. Okay. And your A and B are greater than equal to 0. Now, here your decision variables are basically A and B. Okay, so let's say A is the number of models of type A which need to be produced, and B is the number of models of type B which need to be produced. Okay. Now let's say, imagine that an entrepreneur wants to purchase all of these resources. When I say resources, what I mean is these resources. Okay. So suppose that entrepreneur wants to purchase all of this company's resources, which are to be used for producing type A and type B models. Okay. So if he or she wants to purchase all of the resources, what do they have to know? So that entrepreneur has to determine the price he or she is willing to pay for a unit of each of the company's resources, right? So if they want to purchase all of this machine, labor, then let's say this marketing factors also. So they need to know the price that they want to pay for each of these resources. So in this case, your decision variables are what? Let's say it is U1, where U1 is price to be paid for 1 unit of labor resource. U2 is price to be paid for. Okay, sorry. The first one would be machine time resource, right? Machine time resource. Then let's say labor resource. And similarly, U3 is the price to be paid for 1 unit of marketing factor. So can you tell me what is the objective here? Can you tell me that what is the total price that should be
It would
paid?
be to minimize
Yeah.
the overall price.
Yeah. So just give me the equation. Yeah, you are
So
right.
it would be yes, yes. So it would be like U 40 U1
Absolutely
plus
right. Okay.
45 UT,
Yes.
45 UT, U2 and 12 U3.
Absolutely right. Okay. And from the entrepreneur's point of view, the total cost, right? This cost should be minimized, right? So the
Yes.
objective function, the new objective function becomes minimize let's say some z hash. Okay, that is 40 u1 plus 45 u2 plus 12 u3. So you got the intuition? Now, what are these UIs? Can anyone tell me if from simplex method? Can you relate this to a certain terminology in simplex? Okay, no problem. We will get there. Okay. Now, this is your objective function for the new model, right? But at the same time, there would also be certain constraints. So can you tell me what are the constraints? Divyanshu?
It would
Yeah.
be, yes, ma'am. 2u1 plus u2 plus u3 is
Huh?
equal to 300.
Is
Means
equal to?
300, not equal to, but less than equal to, like,
Y less than equal to?
I'm not sure.
See, that is why I'm saying if you go by the books, you will feel like, okay, U1, U2, U3, on the right hand side, you'll have 300, but then you don't know what should be the sign, right? Why does this happen? This happens when your intuition is not clear. So, for example, okay, see, normally in your book, it will be written if it is a maximization problem in your primal model. For example, here it is your maximization, right? So it automatically becomes your minimization in dual. But why this becomes? That is why I've taken this example so that you can understand and you don't get confused, okay? So verbally, if I have to formulate, okay, so then I will write that, I hope the spelling is right. Uh, yeah, the entrepreneur must offer this company X at least, right? Dollar 300, let's say, for a combination of resources that include, first is 2 units of machinery time, 1 unit of labor, and 1 unit of marketing factor. Because the company, okay, the company could, if it desires, use these resources to produce 1 unit of type A model that is currently generating a profit of $300, right? So since the entrepreneur is offering 2u1 plus u2 plus u3 for all the resources to be used for producing 1 unit of model A, then in this case for the entrepreneur, at least after using the resources, what should happen? The profit should at least be, because it's a profit, so it should be at least 300 or more. So the equation becomes 2u1 plus u2 plus u3 greater than equal to 300. Okay, I will just write it here as well so that you understand later. Since the entrepreneur is offering 2u1 plus u2 plus u3 for all the resources to be used for producing 1 unit of model A, he or she must choose U1, U2, and U3 to satisfy this equation, okay? 2U1 plus U2 plus U3 greater than equal to 300. Divyanshu, are you clear now?
Yes, ma'am.
Yeah. So the same reasoning you will apply. If you apply the same reasoning, you will see that at least same way, $250 must also be paid for the resources used to produce 1 unit of model B. So that is the values of U1, U2 and U3 should also satisfy. What is the second equation? Can you tell me by seeing this?
It would be U1 plus 3U2 should be greater than equal to 250.
Absolutely right. U1 plus 3U2 should be greater than equal to 250. Okay, because you don't have any variable for the third one in the third equation, right? So that's it. Now, what are the values of this UI? Can you now relate what I mean when I say that, okay, this is analogous to something in simplex? What do we call it? See, these U1, U2, U3 are not exactly the cost, right? It is what, okay, go by the definition. What did I say? I said that it is the price to be paid for 1 unit of resource. Now, can you go back to your simplex notes? I'm giving you 10 seconds and then tell me that what is this value exactly? In your simplex method, there are certain terminologies which we had come across. Can you tell me?
Binding constraints?
No, it's a variable, right? How come it's your binding constraint? You don't know whether left hand side would be equal to the right hand side. Think. Goyal sir?
Yes, so I mean these are variables and their value should be greater than or equals to zero. I mean similar to the original problem. I could not understand questions precisely.
I'm saying that there is a terminology in simplex method which is analogous to this. What are you? See, okay, can you tell me what is the meaning of reduced cost?
So
I mean, I have been
so
teaching sensitivity analysis, a simplex method, so you should know by now.
yes, so the meaning of the reduced cost would be that what would be the impact of 1 unit? The change in one variable, then how much cost will get reduced?
What kind of variable?
Decision variable.
Huh?
Decision variable.
No.
No?
Divyanshu, what is reduced cost? I don't think I have the notes in this tab. Otherwise, I could have shown.
Uh,
So it is the rate of change of objective function for a unit increase in non-basic variable. So what is dual
yes, yes,
price?
yes. So it, ma'am, does it corresponds to like your slack and
No, no.
your
How come slack and surplus is here? UI is not even, it is like a decision variable here. But I'm saying it is a decision variable in your dual model. But in your primal, it is something else. How come in primal it will become your slack and surplus? It's not like it's a value that you are adding. Okay, tell me what is the definition of a dual price? We have discussed this a lot of times.
I could understand only one thing, that the dual price, I don't know what the dual price is, but last time you said that the dual price of a non-basic variable is 0.
Dual price of a non-basic variable. Do you have dual prices for basic and non-basic variable? Or you
In
have
the
them for the
previous lecture you said
constraints?
that thing.
But for constraints, ma'am.
Right, right, right. That's the basic difference, right? Now you guys have already covered so much about simplex and sensitivity. Your basics should not be forgotten. So what is the definition of a dual price, Divyanshu?
Ma'am, it is like your optimal solution won't be affected overall,
Who
even
said?
if you change this value. That's what I'm.
No, you have completely confused it with sensitivity analysis and simplex. I'm asking you the basic definition. What do you mean by a dual price? Okay, I think you guys are not taking the classes
Yes,
seriously.
ma'am.
You should
Yes,
please,
yes, yes. Rate of
you should,
change of objective
yeah,
function for every
yeah,
unit increase or decrease
in
in RHS of constraint.
exactly. So these
Yes, I
values
wrote
are
it.
nothing but they correspond to the dual price. They are basically dual prices. Because if you see here also, we are trying to measure, okay, what is the change in objective function for a unit increase or decrease in the right hand side of your primal, right? So technically your UIs are the dual prices, or we also call them shadow price or imaginary price. These are just various names that you have. Or opportunity cost.
So, ma'am, like dual price is that like what change we see in the overall objective function and everything once
Hmm.
if we change the RHS side by a certain
Yes,
unit, right?
yes,
That's
yes,
the overall.
yes, yes,
Okay.
yes. So that is for your primal. But in your dual model, these dual prices will become your decision variables. Okay, simple thing. So this, please remember, this does not measure cost. Okay, but measures potential or we,
Variations.
yeah, exactly. Marginal contribution or variation, whatever you want to call it, to the profit. So your primal model was 300 Na plus 250, 300 A plus 250 B, subject to 2A plus B less than equal to 40, A plus 3B less than equal to 45, and A less than equal to 12. Your dual LP is minimum of Z is equal to 40 U1 plus 45 U2 plus 12 U3, subject to 2 U1 plus U2 plus U3 greater than equal to 300, and U1 plus 3 U2 greater than equal to 350. So from here, you can say that, okay, I'm still audible, right? I don't know, something happened. Okay, so from here you can say, still audible, right?
Yes, ma'am.
Okay, so with every LP maximization problem, there is always an associated LP minimization problem and vice versa. Okay, so therefore, LP problems exist in pairs. Okay, the original problem. So Had your original problem be a minimization problem, that would have been your primal. Okay. Whatever is your original problem is your primal, and the complementary problem is termed the dual. So therefore the dual problem is the same as primal, but it is simply mathematically transformed. You got my point? You are simply just doing a mathematical transformation. So I will just write the definition again so that you never ever forget. Values of the dual variable, that is the dual price, measure the change in value of the objective function of primal when one unit of a specific resource is added or subtracted. Okay. So dual prices can be used for a lot of managerial decision making problems, okay, such as examining the profitability of purchasing additional resources, okay, or evaluating the trade-offs among them. So you can use dual prices. Okay. Now, there are some things to note. Okay. So
And what's the meaning of the term the value of the primal? Does this mean the objective function of the primal or what?
that is nothing but the objective function value of your primal model, whatever is your original problem, right?
Right.
So some things to notice first. Okay. There is a dual variable for every primal constraint. Always. Okay. Just like we saw, you had 3 constraints in your primal model. So you had 3 dual variables, okay, in your dual model. Similarly, there is a dual constraint for every primal variable, okay. So for example, there you had 2 primal variables, A and B. Similarly, you had 2 dual constraints, okay. The sense of optimization is opposite, okay. Always min versus max. The right hand side in primal is your objective function coefficient in the dual, right? For example, you had right hand side values as 40, 45 and 12. So these become your objective function coefficients in the dual, okay? Similarly, the objective function coefficients in primal becomes right hand side in dual, okay? And the coefficient, let's say some Aij of ith constraint of the jth variable in the primal. Okay, so what I mean is objective, not objective function. These are the coefficient of, let's say, the first constraint. Okay, ith constraint of the jth variable. So let's say the first constraint. Okay, and the first variable, you have the objective function, sorry, the coefficient of this a was 2, right? So this will become what? This will come here. So this will become your coefficient of jth constraint. Okay. So when I said A11 was 2. So you won't really see much difference. So that is the coefficient of first constraint of the first variable only. But in this case, it will be ith variable in the dual. We'll see, for example, let's say I say that it is A21. Okay. So here your A21 is how much? 1, right? A21 means coefficient of second constraint of the first variable in your primal. So A21 is 1 here, right? So if you see here, your A12 should be 1. See here, coefficient of the first constraint of the second variable in the dual. Okay. So don't go by the literature, just go by the concepts, you'll be fine. Okay, so that you are not confused. Okay. And another thing is dual of dual is what? Can you tell me what is dual of dual?
Primal.
Yeah, always, right? So it is prime. Okay, so these are some things which you can note. Now, what are the advantages? So why do we do duality? Okay, your second question can come. So first thing first, the relationship between any primal and dual LPP, it gives us very interesting economic insights. Okay, so talking about the advantages of duality. So, okay, before I progress, I just want to see what is your this week's plan that we have to teach. So all you have, all of you have the flyer, right? Okay, so this week we have transportation and assignment problems. Okay. Okay, that is something I'll start tomorrow. No problem. Right. So the advantages of duality are, first is economic insights. Okay. Second is knowledge of duality provides additional insights into sensitivity knowledge. Okay, very obvious. Third is, in some cases, the use of your dual model helps overcome some computer capacity. How? I'll tell you. Computer capacity or any kind of software capacity limitations. Okay. So how does that happen? See, the computational difficulty. Okay, this you can also remember. The computational difficulty of an LP is approximately proportional to m square n. Okay, where m is the number of constraints and n is the number of variables. Okay, so for example, if you see in your dual model, the number of constraints got reduced and you have an m squared to that. So initially you had some 3 constraints. So that was 9 into let's say number of variables you had 2, 9 into 2, 18. Okay, just I'm saying, okay, it's not exactly equal to, it's just proportional to. Now in the dual model that we had just 2 constraints and 3 variables. So that become 2 square into 3, 4 into 3, 12, right? So of course the computational complexity is reduced. And duality theory also gives you the foundation for consideration of several other algorithms, okay, such as MODI, which is the modified distribution algorithm for TP, transportation problem, okay. Then you have column generation, for LP. Then you have dual simplex method. Okay, there is also something called dual simplex method for LP. You can, of course, read all these on YouTube. MODI, I think we'll be covering. Dual simplex is also a very nice topic. I'll try if I can cover. And understanding of this duality theory will generally enhance your general understanding of the structure of a linear programming problem, okay, particularly with respect to their economic ramification. So always remember that uh, duality theory is basically important because it's like you just want to assess the problem in a different light. Okay. Now, there are some example problems that we will solve, okay, because we haven't really solved much, where we will be converting a primal to a dual model. Okay. So let's say your primal LP. See, if it is a completely normal form, now you know what is a normal form. I had already explained before the starting of today's class, right? Here, I had already explained to you what is a normal form. Okay, so I hope you remember. Now, your primal LP is saying max 50x1 plus 40x2 subject to 3x1 plus 5x2 less than equal to 150, x2 less than equal to 20, and 8x1 plus 5x2 less than equal to 300, where x1, x2 is greater than equal to 0. So if you see, this is a normal form of a maximization problem. Now, can you tell me what will be the corresponding dual LP?
So we would be minimizing 150 U1 plus 20 U2 and plus 300 U3. And the constraints would be like such that, so I think it is 3 U1 uh, 3 U1 plus first and second and first plus U2 should be greater than or equals to 50.
Plus U2, where is U2? Why should U2 come?
Not I did not understand this aspect clearly. So how to
Here, let's say you have U1, U2, U3, right? Where U1, U2, U3 are unit prices of each of the ith resources, right? So if you consider for the first one, when I'm saying U1, you just have to concentrate on the x1 values. Do you have any x1 value in the second equation? No. So there wouldn't be any value corresponding to that. So it will be simply blank. And it would be 8U3 greater than equal to 50. Okay.
right?
Similarly, you will have 5U1
5
and U1, U2, U3 would be greater than equal to 0. Okay. Now see, this was very easy because this was in a normal form, right? But you might not always have it in a normal form. Okay. So let's say, so this was the first example. Okay. Now the second example that I'm giving is minimization of 2x1 minus 3x2 subject to x1 plus 2x2 less than equal to 12, 4x2 minus 2x2 greater than equal to 3, 6x1 minus x2 is equal to 10, and x1 and x2 is greater than equal to 0. So can you tell me why is this not normal?
Because of the first constraint, and probably because of the third constraint as well, which is
Absolutely right. Right. So in a minimization problem, okay, your constraints have to be greater than equal to constraints, right? But as you can see, it is not. So if I have to convert this, okay, first I will, let's say, convert this. See, I will give you the shortcut methods also, but let's go by the standard. First, we want to convert this to a normal form. So if I have to convert this to a normal form, how will it look like? This will remain the same, minimization 2x1 minus 3x2. Now, if you want to convert the first constraint to a greater than equal to constraint, how will you do it?
multiply both the sides by -1.
Absolutely. Minus x1 minus 2x2 greater than equal to minus 12. Second one remains the same. 4x, okay, I think this should be 4x1. Okay. Second one remains the same, 4x1 minus 2x2 greater than equal to 3. What about the third one?
So this is both less than and then equal, greater than.
Yeah. So one is less than. So this you can write as one is 6x1 minus x2 less than equal to 10. Another is 6x1 minus x2 greater than equal to 10, right? So 1 though is in normal form, so that I can write 6x1 minus x2 greater than equal to 10. What about the other one? How do I convert that? Again, same logic. By? Yeah. So minus 6x1 plus x2 greater than equal to minus 10. And x1, x2 is greater than equal to 0. So now you have a normal form. And now if I have to convert from here to a dual LP, so this is your normal form of a still a primal model. And now if I want to convert this to a dual LP, what will it be?
Minus 12 u1 plus.
No, first tell me the objective function.
Objective function is minus 12 u1 plus.
No. What is the nature of the objective function?
Oh, maximize.
Yeah,
Yes.
yes. Always say that, okay? Max.
Minus 12 u1 plus 3 u2 plus 10 u3 and plus minus 10 u4. And such that the constraints would be minus u1 plus 4 u2 plus 6 u3 plus minus 6 u4 is less than or equals to 2.
Very good. Yes.
And
Same thing
minus
here also. And u1, u2, u3 and u4 is greater than equal to 0. So always remember, for converting your primal to a dual, okay, if it is a, you first have to check if it is a normal form or a non-normal form. Okay, if it is a normal form, it is very straightforward, right? But in case it is a non-normal form, there are two ways. One thing you can do is you can completely convert it into a normal form, or there is another shortcut, which is something that now I will discuss. Now, let's say there is another kind of problem, okay? Let's say now your primal is max 12 u1 plus 3 u2 plus 10 u3 subject to u1 plus 4 u2 plus 6 u3 less than equal to 2, 2 u1 minus 2 u2 minus u3 less than equal to minus 3. But now your u1 is less than equal to 0, u2 is greater than equal to 0, u3 is unrestricted in sign. Unrestricted means it can be either plus or minus. So now if you see, It is a maximization problem. Okay. But the only difference is that now your variables are not non-negative. So this is again a non-normal form, right? Because your variables are also supposed to be non-negative. So how do you tackle such problems? So I will just give you a very simple cheat sheet, okay, which is something you can carry in for your entire life. So the cheat sheet is, okay, for a primal to dual conversion, okay. If your primal is max, okay, always remember, in case your primal is minimum, whatever rules I'm writing here, it will exactly be the opposite, okay. Then your dual becomes min, right? Now, the first thing is, if the ith constraint in your primal model is of a less than equal to type, then your dual variable ui would be greater than equal to 0. Okay. Similarly, if your ith constraint is greater than equal to type, your dual variable ui is less than equal to 0. And if your ith constraint is of an equality type, then your dual variable is unrestricted in sign. Same logic. If your primal variable xj is greater than equal to 0, here but your ith constraint would be, jth constraint would be greater than equal to type. Okay. If your primal variable xj is less than equal to 0, your jth constraint would be less than equal to type. And if your primal variable xj is unrestricted in sign, your jth constraint would be of an equality type. Okay, so this is the simple cheat sheet that you can just remember only. You can simply remember, I'll tell you, only the first line, this one and this one. See, because for an equality, it's very simple. If it's an equality in both the cases, on the other hand, it would be either unrestricted in sign, okay, and vice versa. But if it is a primal max problem, and if the constraint is a less than equal to type, then your dual variable is greater than equal to 0. But if your variable is greater than equal to 0, your corresponding constraint in the dual would be of a greater than equal to type. Okay, only these things you need to remember. So if I have to solve this now, okay, now observe closely. See, first thing first, what will I write is I will write first, I'll just simply write all the equation. Okay, so I'll simply write my objective function first. So minimize, what will it be? Okay, so let's say here my xj's are the dual variable, okay, or maybe you will get confused. Let's say some p1, p2. Pi is my dual variables, okay, because I have these variables in my primal model, okay. So now I simply write what? Minimize. So how many constraints will you have in your dual model?
So since there are three variables in the
Yes,
objective
exactly. So
function,
you'll have three constraints in your dual model, right? And two decision variables. So minimize 2p1 minus 3p2.
P2.
Okay. Subject to Now I will simply just write the equations first, okay? But not put any sign. That is the first thing that you do when trying to formulate a dual, okay? So subject to here, I'm keeping the cheat sheet also so that you can understand. Subject to, for the first one, P1 plus 2P2, I'm giving nothing, 12. Then 4P1 minus 2P2, 3. 6P1 minus P2, 10. And P1, P2 and P3. There would be some sign. Okay. Now let's use this. Your primal is a max model. So first criteria is met. Okay. When your ith constraint, see in the first constraint, if you see, first constraint of your primal model is a less than equal to type. So the corresponding dual variable would be how much? Sorry, this should be only P1 and P2, right? Yeah. So your first variable would be greater than equal to 0. So since this is a less than equal to type, P1 is greater than equal to 0. Second constraint is also less than equal to type. So P2 is also greater than equal to 0. That is it. That is done. So you have now decided what will be the signs. Okay. Now talking about the constraint. So U1 is less than equal to 0, right? So that means here it is saying primal variable xj is less than equal to 0. Then your corresponding constraint would also be less than equal to type. So the first constraint is less than equal to type. Second one is greater than equal to 0. So it is greater than equal to type. Third one is unrestricted in sign. So equality type. Okay. So you got it.
But then in this maximization problem, and which is okay, this is in the normal form, and so here, but then we get whatever dual form we are getting. This is not in the normal form.
That is also a non-normal. Yes. But it will give you the same logic. So this is like a bypass, okay? Because you convert this into a normal form, then again you do it. It's strenuous also. Plus sometimes you know what, it becomes very difficult to understand also, because if you have to convert that into a normal form, your U3 further has to be, I mean, divided. Okay, so let's say U3 is some x1 minus x2. Now that x1 minus x2 can be greater than equal to 0, or x1 minus x2 can also be less than equal to 0. Okay, so you will have to define two additional constraints, and that further just introduces complexity of the model. So in order to just bypass that, we can use this simple cheat sheet and then just arrive at the values, just like I explained. But now let's say, okay, we will also solve another example so that it's more clearer to you. Okay, so this
But
was
then
where we are. Yeah, what?
so since now this dual LP is in the non-normal form, so while applying the simplex method,
I'm
do I
not able
still
to
need?
hear you. What?
So then, I mean, to solve this dual LP, say if we are
Uh-huh.
solving it using the simplex method, then do we need to bring it in the standard form again, or the simplex method for the dual
See,
will
if you
work
do
ideally?
it manually, you need to. But if you just simply code it in the Python, you don't need to. You simply need to write your model. Manually, if you do, then yes, you will have to convert this into a standard form, and using simplex method, you will have to solve. Okay. But there is also something known as dual simplex method. Again, that's a simplex logic only, so you will eventually have. But yeah, that is only for hand calculation, and that is for your basic understanding. Okay. So it's always like, see, there is a lot of theory behind everything and anything which is coming up, okay? But anyway, nowadays you don't even need, you have all I mean, the entire coding environment is available to you, and you can simply just plug in your equations and get the values, okay? So we will solve two more problems so that it's very clear to you, okay? So my fourth problem is, let's say, uh, okay, maximize x1 plus 2x2 plus 3x3 subject to x1 plus x2 less than equal to 2, x1 minus x2 plus x3 greater than equal to 1, minus x1 plus x2 plus x3 is equal to minus 1. And x1 is unrestricted in sign, x2 is greater than equal to 0, and x3 is less than equal to 0. Okay. So now if I have to convert this into a dual LP, okay, So first thing first, so we have u1, u2, u3. So minimize 2u1 plus u2 plus u3 subject to u1 plus u2 minus u3. You just put 1 plus u1. Forget it, why am I writing person? u1 minus u2 plus u3, 2. There is no u1. u2 plus u3 is 3. And you will have to decide the values of u1, u2 and u3, okay? So first thing first, in my first constraint, ith constraint is less than equal to type, okay? So my jth variable or the ith variable in the dual model would be greater than equal to 0.
Yes. U1 is greater
So,
than
Ma'am, please repeat.
yes. Huh? Yes,
Ma'am,
Divyanshu,
please
were you saying?
repeat. Yes, ma'am, because I was confused, like how we are defining the signs for each one.
This is the cheat sheet, right? So the first constraint is a less than equal to type. See, the first constraint is a less than equal to type. Then your corresponding variable would be, dual variable would be greater than
Greater
equal to
than
0.
equal to.
So my first constraint is a less than equal to type. So my corresponding dual variable is a greater than equal to 0. Okay. Second constraint is a, so whatever be the sign of your constraints, okay, in your primal, if it is a maximization problem, then in the dual model, the signs will completely be the opposite. Just remember that. So u2 would be less than equal to 0 and u3 would be unrestricted in sign because it is an equality constraint. So whatever be the sign of your constraints in your primal LP, the opposite would be the signs of the dual variables if and only if your primal is a maximization problem. I'm repeating this, okay? But so the opposite would be true. Now, for this one, x1 is unrestricted in sign. So that means equal to. x2 is greater than equal to 0. So primal variable, if it is greater than equal to 0, your jth constraint would also have the same sign. So this is greater than equal to, and x3 is less than equal to 0. So this is less than equal to. And that's it. Your dual model is there. Found. Clear, Divyanshu?
So, so it's clear. So it's that your constraints would define the dual models, your
Prime,
non-negativity constraint, right?
yes,
And
yes,
your
yes, yes. The constraint signature, matlab nature of
yes,
sign,
yes,
yes.
yes. And your
Okay.
primals
It is
non-negativity
like
clause would
completely the
define your
opposite.
dual.
So,
Yes.
yes.
Okay,
So,
okay.
so if your primal variables is greater than equal to 0, your corresponding dual constraint is also greater than equal to type, provided your primal is a max. Okay. Now we will simply solve a different type of a question, which is now your primal is a min. Okay. So minimize 15x1 plus 20x2 subject to x1 plus x2 greater than equal to 90. 3x1 plus 2x2 greater than equal to 150. x1 minus 3x2 less than equal to 25 and minus 2x1 plus 5x2 is equal to 25. Okay. And x1 is also greater than equal to 0 and x2 is less than equal to 0. But now all the logic would be reversed. So now it is a min problem. So anyway, it is a max problem. Okay. 90 u1 plus 150 u2 plus 25 u3 plus 25 u4 subject to u1 plus 3 u2 plus u3 minus u4. This would be 15. Then u1 plus 2 u2 minus 3 u3 plus 5 u4, that would be 20, and you will have to determine the signs of u1, u2, u3 and u4. Okay. So see, again, the first constraint is a greater than equal to type. So technically, if your first constraint is a greater than equal to type, your dual variable is less than equal to 0, but only if your primal is max. since your primal is min now, it would be of the same sign. So that would be greater than equal to 0. So whatever be the signs of your constraints now would be the same signs of your dual variable. So this would also be greater than equal to 0, this would be less than equal to 0, and this would be unrestricted in sign. And now whatever is the sign of your primal variable. So if your primal variable is xj greater than equal to 0, your jth constraint was greater than equal to type. But now your primal is min. So it will be completely ulta. So here now it would be x1 is greater than equal to, so this would be less than equal to. x2 less than equal to, so this would be greater than equal to. Okay. So that is what I wanted to tell you. So that cheat sheet which I have given to you, okay, don't follow it blindly. It is only when your primal is a maximization problem. Do you want to solve one more problem like this, or is this fine?
So probably there is some mistake, some typing mistake in the first constraint. It should be minus 2u4.
What? I didn't get you. What?
So the first constraint of the duality here would be u1 plus 3u2 plus u3 minus 2u4.
Oh, right. Thank you. Yes. Yes, minus 2u4. Yeah. So do you want to solve any more problems like this, or is this fine?
It's fine, I guess, but then
I think, yeah.
for the meaning, everything is reverse. So this is slightly difficult to remember.
Yeah, I think, yeah. So you can always go back and, like solve more problems of this nature. Okay, you can also try to do is, okay, maybe I can, but for that you will have to do something. Okay, this is a small homework for you to understand. So just do this, okay? After this class, you will understand what I want to tell you. So let's say you have a maximize 50x1 plus 40x2 subject to 3x1 plus 5x2 less than equal to 150, x2 is less than equal to 20, and 8x1 plus 5x2 less than equal to 300. And x1, x2 is greater than equal to 0, okay? So your corresponding dual would be minimize 150 u1 plus 20 u2 plus 300 u3, okay? Subject to 3 u1 plus 8 u3 greater than equal to 50, and 5 u1 plus u2 plus 5 u3 greater than equal to 40. u1, u2, u3 is greater than equal to 0. What I want you to do is solve, okay? My God. Yeah, solve both using simplex method, okay? And at the final iteration, whatever the final table that you get, okay, you will see that whatever is the value of your ZJs, okay, that would be the value of the basic variables in your dual model. And I want you to verify that, and I also want you to verify how much is the objective function value that you are getting. So you will see that the objective function value of primal is always equal to the objective function value of dual at the final iteration, if you have a feasible and optimal solution. In case you don't have, you won't get an optimal solution, but usually it is the case. So I want you to go back and verify that. Is that okay?
Yes.
Okay. Now some relationships which I want you to know between a primal and a dual is, so the first was this, as I already wrote. Okay, this is something that I want you to verify. Okay, using both these models. Okay, solve using simplex, simple simplex table, whatever you have left. Okay. Second is, if the basic solution of a primal is optimal, then the corresponding dual solution is also feasible and optimal. Okay. But if the basic solution of a primal is feasible but not optimal, then the corresponding dual solution is infeasible, and vice versa. Okay, so these are just some relationships I wanted you to know. And okay, so at the optimal solution, I already told you what will happen. Okay, there is something also known as, you can read about it. Okay, so duality gap. Okay, so what is a duality gap? So if, let's say, some x1, x2 till xn is any feasible solution to the primal, which is a maximization problem, okay, and u1, u2 till um is the corresponding solution of dual, which is a minimization problem, then c1 x1 plus c2 x2 till cn xn would always be less than equal to b1 u1 plus b2 u2 plus till bm u1. So what I mean is, before reaching the optimality, okay, at the optimality anyway, it will be equal to, okay, but before reaching the optimality, at any stage of the iteration, you will see that the objective function value of the primal, if it is a maximization problem, is always less than equal to the objective function value of the dual. So at any stage of the iteration, the difference between these two is called the duality gap. And this is actually given by the weak duality theorem. Okay. Similarly, this is stated by your strong duality theorem. Okay. This is just for your basic understanding. Okay. There is also something known as okay, I'll just explain that as well. We call it complementary slackness. Okay. So what is complementary slackness? So that is if E1, E2, okay, till En are n excess variables. Okay, slack surplus variables, you can say, of the dual at optimal solution, then ei into xi is equal to 0. So always remember, for all I equal to 1 to n. So it's like either the decision variable in your primal is 0 or the corresponding slack or surplus is 0. So this will right now appear very I mean, what should I say, on the, like, kind of like an on the surface. So this basically implies that either E1 is 0 or Xi is 0 or both are 0. So that basically means that Ei and Xi cannot be positive. Okay. Now, one example which I can give you is, so this property, okay, it is very important. This is a very talked about property. It is important in verifying whether a feasible solution is optimal for the primal problem or not. Okay. So here we assume that the given feasible solution is optimal. Okay. And we try to construct an optimal dual solution using the complementary slackness conditions. So if we are successful, then the given feasible solution is in fact optimal for the primal. Now, you remember non-binding constraint, right? So what is the dual price of a non-binding constraint? I'm just trying to give you an example. Can you tell me what is the dual price of a non-binding constraint? It's zero, right?
Zero.
But what is the slack or surplus for that constraint? That has some value, right? Because it is a non-binding constraint. So see, that is also satisfying the complementary slackness condition. Okay. So like that you can relate. So just a small diagram which I would want you to visualize. Okay, this is about simplex and dual simplex procedures. Okay. So let me not draw the box first. So this is your optimal and feasible solution, which is the final solution. Okay. This is optimal but infeasible. And this is non-optimal but feasible. So if you remember, we always start our simplex with a feasible solution, right? So your simplex starts here. And then slowly we go to the optimal and feasible solution. Okay. Very bad. I need. But your optimal but infeasible, say it will start and finally reach optimal solution. So here is where your dual simplex starts. So you can actually check any YouTube video on how is a dual simplex, because due to the brevity of time, I won't be able to cover it in this class. So I just want to give you the, should I say, the understanding of how things are working. So yeah, I think that was about the duality theory, which I wanted to say. And okay, I guess that's it for today. I'll just stop the recording.